so we talked about that carbon has two isotopes. It's got I mean, their masses. One of them is more abundant, that's carbon 12, that's 99% probability, and carbon 13 is only 1%. So if a molecule has carbon 13, it will have a mass of 17. If this molecule has carbon 12, it will have a mass of 16. But mostly it's the higher chance is for 16. So your detections, it would be 99:1. More of carbon 16 would be detected. But if you have two carbon atoms, then the probability of getting the M peak decreases. Why? Because carbon 12 and carbon 12, its probability decreases to 98%, while the probability of getting one carbon 13 slightly increases to 2%. And as you get more carbon atoms, the probability or the ratio 97:3, it becomes 97:3. And I told you about the formula. We talked about the formula. How do you figure out the number of carbon atoms? You just input the M+1 and MP, and we did some past paper questions as well. Now the next thing we'll move towards mass spectroscopy is fragmentation. I told you that whenever you have a molecule, it breaks down into very, very tiny fragments. So for example, this is an example. Like if I have a molecule CH3 and Cl3, CCl3+1. This molecule will break down into many tiny pieces. So maybe it breaks down into a CH3+1 fragment. Maybe it breaks down into a CCl3+1 fragment. Maybe a carbon atom breaks off. Maybe a Cl atom breaks off. Maybe there's a carbon with two hydrogens that breaks off. So whatever happens, you get these tiny fragments, and you get all these detections at different smaller masses. I mean, for example, CH3 would happen at 15. So you would detect something at 15. You might detect something at 14 as well. You might detect something at 12, or maybe what is CCl3? That's 35. That's 105 plus 12. That's maybe there's a detection at 117. So you get all these smaller peaks. You have a heavy isotope, heavy molecular ion, and you've got all these tiny fragments. Now the point I'm trying to make is that these tiny fragments, they can help you identify the structure of the molecule. Sometimes, not always. If you know the masses of the tiny fragments, you'll be able to figure out the structure or the arrangement of the molecule. So here's one example. So this is one example that somebody did mass spectroscopy of a molecule, and that molecule is X. So we don't know what this molecule is. Anyways, you got a bunch of smaller peaks or having smaller masses. There was some detection at 14. There was some detection at 16. Then there was a detection at 28, then 30, then 44. That happened to be your molecular ion. Now, by looking at the smaller particles, you can get small glimpses on what the original molecule looks like. You might get some information about what this actually looks like. It's like a puzzle. If you can sort of figure out what these smaller structures are, you can kind of figure out the bigger structure as well. So you start off with the smallest piece. If you look at 14, you would realize that the smallest piece, what atom has a mass of 14? That's nitrogen. Is that clear? So let's assume we don't know any of these. So when you see something at 14, so what's your guess? It's probably going to be nitrogen, right? Is that clear? I said then you're getting some particle which has a mass of 16 as well. So you would think that 16, who has a mass of 16? That's probably going to be an oxygen atom, right? So you start off with the smallest pieces. And then using those smaller pieces, you start making up the bigger pieces. Remember, the bigger piece is basically a combination of the smaller pieces. So what do you think is 28 then? Like 28 would probably be two nitrogens joined together, right? And then you have 30 as well. What could be 30? 30 could be a combination of these smaller pieces. It could be a bigger piece. It could be N with O, that's 30. And then you finally try and figure out what this bigger structure is. So for example, if it's 44, then it's going to be two N's and one O. That's how you're going to get 44. Now remember, these smaller pieces are a part of the bigger piece. Like the N2 can be, this molecule can break down to produce an N2 ion. An NO particle could also be produced when this fragments. A fragmented piece of this molecule would give you NO. The nitrogen and oxygen particles would also be detected. So the idea is that if you start looking at the smaller particles, you'd be able to figure out the bigger particle as well. Is that idea clear?
Yes, sir.
ठीक है, बाकियों clear? Bhaskar, is this clear? Alicia?
So can you explain this again?
नहीं, mass spectroscopy का पता है क्या है वैसे?
जी आपने एक क्लास में दी थी.
हाँ, अच्छा, so what happened in mass spectroscopy was that you had a big molecular ion. That was the molecular ion. We were focusing on the molecular ion, but now we are focusing on the fragments. That I told you that when you do mass spectroscopy, okay, so when you, so I told you, when you do mass spectroscopy, not only do you have molecular ions, but you have the molecule breaks down into small tiny pieces. Okay. And that piece is a part. Bhaskar, I'll answer that. Okay. So this thing, these small pieces would be detected. Now, it's just like a puzzle. Like if you see small tiny pieces of puzzle, you can try and join them together in a way to make the big thing. But that will not always happen. It's like solving a puzzle. I said, so coming back to this, this was the mass spectrum given for something, for some molecule X. And I was told, I wasn't told anything. I was just told that there were different particles being detected at different masses. So 14, you look at the tiniest particle.
So आपकी आवाज glitch कर रही है.
नहीं, अभी ठीक है? नहीं, is this clear? अभी सही है या नहीं? Saim, can you hear me? Munya, can you hear me?
Yes, I can hear you.
Okay.
It's clear, sir.
So, Bhaskar, why did I not take this as? Why did I not? Your question was, why did I not take this as CH2 plus, right? So the answer is that if I had a CH2 fragment, then wouldn't the CH2 fragment break down further and might give me a carbon fragment?
Yes, sir.
So I should have gotten something at 12 as well. Bhaskar, is that clear?
Okay, yes, clear.
So the point is that it's probably not going to have. It's not going to have CH2. So anyways, by looking at the smaller pieces, you can figure out the.
So can we say that the first fragment that we get would always be the element?
Yes, we can kind of,
Okay.
not all, because remember, not always. Okay, make sure. The reason you're going to say not always is because you don't know how the fragmentation is happening. I told you that fragmentation is completely random, right? Is that clear?
Yes.
So maybe you're going to get carbon and maybe you won't. Okay. So that's not 100% true. So even your scenario, that even if we take that, most likely the most likely scenario is that it would be the elements, but let's, even if we take CH2 as this being CH2, then we'll be stuck with 16. What is 16? If it's CH4, then the molecule is complete. It would be harder to actually figure out 30. It wouldn't make sense if you start off with carbon. Is that clear as well? So you'll go for the most probable scenario.
Yes, sir.
Okay. So now here's a
So
question.
for 28,
Huh?
for
Not-
28, I mean for the MR 28. I mean you said if it was 28 could be N2 positive ion, right? तो मतलब 28 तो दो nitrogen atoms भी हो सकते हैं, लेकिन on the other hand एक molecule, I mean one atom in the periodic table could have MR of 28, तो वो भी तो हो सकता है.
Okay, that is a possibility. It's like who has an MR of 28? I don't think anyone has an MR of 28, but that is a possibility. Yes. Okay, like in the
तो
most
वहाँ पे
नहीं,
नहीं, तो
but
at that point how do you differentiate it?
no, but the most likely scenario comes out to, because it's a 44. Like who's 28? Just a second. Or anyone who's 30. I don't think anyone is 28 or 30. Just a second. 24. But anyway, it's oh no, that was silicon is 28. Okay, so silicon is 28. So if this was silicon, then I mean this would still not make any sense. I mean, the most likely, the most feasible ones, the most probable I'll add to this, okay? I'll just add to this. The question will not be this open-ended, okay? Because if I remember clearly, this particular question, I think, I mean this one specifically, where they ask for the identification of N2O. So it's not going to be a completely open-ended question. If I remember correctly, they probably gave us ammonium nitrate and it was kind of decomposing. Is the idea clear? Okay, the starting point of the question was that, so it's not going to be a completely open-ended question, just like the next one. I mean, if I remember correctly, in the next one, they clearly told us that whatever the molecule is, it's got silicon, chlorine, and oxygen, and it had no isotopes. Silicon was 28, chlorine was 35, and oxygen was 16. And what happened was that you got all these detections at these mass numbers. So all of these, so you got various detections. At these mass numbers. So you're going to start off with the smallest, and they've already told us. So again, it's not an open-ended question. So they've already told us that it contains silicon, chlorine, and oxygen. So the first part is, what is 133? I mean, like it's probably something that has silicon, chlorine, and oxygen in it. And remember, in this question, they were asking to draw the complete structure, not just the formula, but the whole structural formula. So what do you think is 133, the smallest fragment? What combinations of atoms would give you 133? I mean, you use your calculator if it's
Chlorine and silicon, 3 atoms of chlorine and 1 atom of silicon.
okay, so it's going to be, so if you sum this up, 28 plus 35 plus 35 plus 35, that would give you 133. And remember, the fragments will have incomplete bonds. They would be ions because they've broken pieces of the bigger molecule. And so what do you think is 149 then? Like, what's the difference between 133 and 149?
7 plus 9, 16.
So this thing has a difference of?
16.
So what is 16?
Oxygen.
So that means what 149 is basically, it's basically a silicon with Cl, and then there is an oxygen as well. And that's the fragment. Okay, is that clear? Was that clear, Ibrar, Aisha, Alicia?
So you said that every of the fragment would be have an incomplete bond. So sir, in the second one, oxygen.
No, oxygen is not making two bonds.
Yeah.
Okay, it's going to have incomplete bonds because वो उसका piece टूटा है ना original का, so its bonds are incomplete. Like where is like all of them, if I break this into pieces, so it's always going to have incomplete bonds. Okay, is that idea clear? If the carbon breaks off, the Cl atom breaks off, it's not going to have complete bonds. Okay.
Yes, sir.
So the next thing is we have so we figured out 149, right? Then I have to
130. Yeah, first you figure out with them. So I mean, there could be situations where there could be different combinations जहाँ पे molecules एक ही number बना है. For example, 133 SiCl3 बना रहा है. Let's suppose SI.
नहीं क्या बता रहे? ये बताओ जरा. पहला वाला.
For example, 133 is being made by SiCl3. On the other hand, शायद ये possibility हो कि just in case there were some other atoms के SiO2N, for example, let's suppose वो भी 133 बना रहे हैं और ऐसे 2-3 ऐसी possibilities वही molecule में तो 3 possibilities हो एक ही number के.
हाँ, but that is possible. ठीक है. That is possible, but I don't think that they will give you such an open-ended question. Okay. I mean, that is possible. And remember this thing, this is not done. I mean, computers actually do this. Okay. Computers actually do this. Because there's so many combinations that they actually figure out and they try to build on the model and then they try to figure out 396. So for you, the questions would not be that open-ended. Okay, is that clear?
Yes. Okay.
The next one is that's why you study isomers a lot, because I'll explain isomers, because a lot of times what you'll do is you'll try and mix and match. You'll try and so we'll talk about that in a bit. Okay. Achha, what's 247? What's the difference between so 247 is a bigger fragment. So what's the difference between 149 and 247? That's I think 98. So what could be 98? Like you need to add 98 to this, you'll get to 247. Okay, that would be an even bigger.
2 chlorines, 1 silicon.
Okay, so you already have 3 Cls and 1 oxygens. And what you're going to do is if you add another silicon and 2 Cls, that would give you, I mean, the bond is incomplete, that would give you 247. And then 263, that's another addition of 16, which is oxygen. So you got oxygen, and there's a difference of 133 at the end. What is 133? That is
another molecule of chlorine and silicons.
Okay, it's SiCl. 3, right?
Yes, sir.
So anyways, you've figured out what 396 stands for. 396 stands for this entire big piece of molecule. Okay, is that clear? So the idea is smaller pieces, you can sort of put them together to make bigger pieces. Bigger pieces can form, you can put them together to form the original molecule. Okay. So is this part clear?
Yes, sir.
So now I'll also talk about this thing. Maybe somebody figures out. Not sure if this would be a proper question. I'll probably change the question if it's not. Let me just think. No, it looks like I think it would work. So I'm just making up a question. So the question is, you figured out that there was an M peak, right? And the M peak of the M peak was coming out to be, so there's a question, the M peak is at, assuming the carbon isotopes, it's C3H7OH. So it had a mass of what? What's 3 carbons? That's what's the MR? 3 carbons, 36 plus 16. That's 52 plus. So is this 60? Can somebody confirm this?
Yes, 60.
So this is 60, right? Now you've been able to figure this out. Maybe you did some chemical tests and you figured out that this comes out that this is an alcohol, but simultaneously you did a mass spectrum, right? And it came out to be 60. Now you can't really figure out which alcohol is this. I mean, is it a primary or is it a secondary alcohol? That's the question. So that's where your knowledge of isomers comes in, because isomers are helpful. That's why you study isomers. Isomers are helpful in figuring out how many possible structures could this molecule have. So it could either have an OH at the end with the hydrogens over here, or so maybe the question would work. I'm still actually doubtful if the question works. But anyways, this one. So you could get these 2 structures, right? Okay, sorry, let me change the question completely. I know a question that will work. Just a second, very quickly. Let's forget this. So it's the molecule is C3H6. So it's propene. That's 36. That's 42, right? So you figured out the number of carbon atoms. You figured out that it's C3H6. Now there are 2 types of C3H6. There are 2 isomers. It's either going to be propene. So that is one possibility. Or the other one is that it would be a cycloalkane with hydrogens attached to it. So that's also C3H6. Now the mass spectrum will give you an idea which of the isomers it is. So the fragmentation pattern, I mean, the molecular end peak would be the same because the mass is exactly the same. So the fragmentation pattern, which fragment do you think is going to exist in this molecule or could be produced by this molecule and will not be produced in this molecule? Like what fragment would be detected if it's this one, and what fragment would be detected if it's this one? Okay, which one has a uniquely identifying fragment?
The first one.
Okay, what is the fragment?
It could be C double bond C.
It's going to be C double bond C. If it's C double bond C, but the point is mass spectrum looks at the mass. The mass would be 24, right? So in the mass spectrum, you don't know what the structure is. You just know that it has a mass of 24. You can get a fragment of 24 over here as well, right?
G.
So the mass spectrum will not be, the double bond will not be visible in the mass spectrum. So this fragment that you talked about, you're going to see that fragment in both of them. I mean, the fragment having a mass of 24 can exist in both molecules. So what is that fragment that will exist in this molecule and not in the other one? The fragment that will have a unique mass. So what if
CH3.
So what if I have CH3 plus 1 fragment, right? So that has a mass of 15. So if I look at the mass spectrum, I'll be detecting something at 15. So there would be something getting detected at 15. Can I get a fragment of 15 over here? I mean, the molecule will break into smaller pieces. Can it break down into a piece which has a mass of 15?
No.
Okay, that's not possible. You're either going to get 14, right? But you're never going to get 15. So in this case, there is no fragment that has a mass of 15. Okay, so yeah, is the idea clear that even the fragmentations, because remember you're playing a guessing game. Even if you've guessed the number of carbon atoms, the number of chlorine, and the number of bromine atoms, even then there are a lot of possible molecules, right? There are a lot of possible structures that could exist. So what you'll do is you'll try and do further guesswork. You'll try to check which isomers are possible, which ones are not possible. Okay, is that clear?
Yes.
So now the next thing, so we'll move on now. Okay, that's about it. There's not going to be any big questions. They're just going to tell you to count the number of chlorines, bromines, and the number of carbon atoms, and then they'll give questions on the fragmentation pattern. The next thing that we're going to talk about is called Hnmr. Okay, that's something that's closely linked. It's another analytical technique. It's got nothing to do with the one that we just studied, but the two techniques work together. All analytical techniques actually work together. So Hnmr is known as nuclear magnetic resonance. And what happens in Hnmr is that the entire focus is on determining the hydrogen environment the entire focus is on determining the chemical environment of the hydrogen protons. The chemical environment of hydrogen protons. So what happens here is the focus is on hydrogen and its environment, how it's bonded to other elements. So if you look at a hydrogen atom, it's got exactly one proton. It's got an odd number of protons. Forget that it has an electron at the moment, but this is what a hydrogen nucleus looks like. Now, every elementary particle has a magnetic field. So the same happens with protons. Protons, they have a magnetic spin, just like electrons have magnetic spin. So there's an associated magnetic field that's associated with the proton. Think of it as a tiny magnet. A lot of times when you have even number of whenever you have even numbered nucleons, then what happens is in even numbered nucleons, the nucleons are all paired. Which is why they don't have a net magnetic field, because if one of them has a magnetic field in this direction, the other one has a magnetic field in the opposite direction. The same happened to electrons as well, that their magnetic fields were all paired. So which resulted in no net magnetic dipole. Is that clear?
Yes, sir.
So most atoms are not magnetic. Most atoms have even numbered. Most of the common atoms, carbon is 12. Carbon has 12 nucleons. Oxygen has 16 nucleons. Similarly, the other ones as well. Sulfur has 32 nucleons. So most of them, they don't have a net magnetic dipole because their nucleons are all paired. but not hydrogen. Think of hydrogen as a small, tiny compass needle, which has a magnetic field. And this compass needle could point in any direction. Just like a compass needle, like if there is no external magnetic field, it could sort of spin around. And the needle could point in any direction that it likes. Is that clear?
Yes, sir.
So now, if you've seen an MRI scanner, an MRI works its magnetic resonance imaging, or which is the same thing. Like an MRI scanner, what they do is they put things into these giant, like if you can see this over here. So there's this big giant magnet. I mean this one. So you put, I mean, in this case, you put the person inside a big giant magnet. The person has a lot of hydrogen protons. Like we have a lot of hydrogen protons. Any organic substance has a lot of hydrogen protons. So you put that person or thing or molecule that has these hydrogens, and they place them in a magnetic field. So they're these big giant magnets, really powerful. And the molecule is placed in that. So let's think of a small, tiny molecule of, so let's think of a tiny molecule of ethanol. And also at the same time, think of the hydrogen protons. So one of the magnet would be the north side, the other one would be the south pole. And all these hydrogen protons, they have these tiny magnetic fields all randomly pointing in different directions. But what happens if they are placed in a very powerful external magnetic field? What happens to a compass needle on planet Earth? Where is it pointing? If in the presence of an external magnetic field, it will point, or it will align itself with the external magnetic field. Is that idea clear?
Yes, sir.
Sir, अभी in this case ये क्यों align नहीं कर रहे? I mean, why are
they are aligning. I'm just turning them around. Is that clear? So they would all align with the. So they're going to all align with the external magnetic field. All of them. This one would also. So is the idea clear that the hydrogen proton, the nucleus of the hydrogen proton has this tiny magnetic field. When you place it in a powerful external magnetic field, its magnetic field direction aligns with the external magnetic field, just like a tiny compass needle. Is that clear?
Yes, sir.
So that's known as the low energy state of the hydrogen protons.
Sir, what would happen if हम दोनों north कर दें?
नहीं यहाँ पे?
If we place the molecule between two north poles.
Both the magnetic, I mean the external magnetic field will get cancelled out.
Repulsion.
External? I mean, फिर तो यूं होगा कि the magnetic field of the hydrogen atoms would be either pointing upwards or downwards, क्योंकि वो तो एक डायरेक्शन में भी पॉइंट नहीं कर पाएंगे.
नहीं, the first thing is the external magnetic field would cancel out to begin with. Idea clear? I mean the north, if both of them are north, they're going to cancel each other out in the middle.
जी अच्छा.
वो तो तुम बात करो कि अगर वो exact middle में नहीं होगा ना, फिर it might point upwards or downwards, right?
जी.
But if it's right in the middle, the two magnetic fields would get cancelled out.
ठीक, okay.
So anyways, this is known as the low energy state. Low energy state is your aligned spin. Remember, magnetic field is known as a magnetic dipole is known as a spin, or we can call it a magnetic dipole. Okay, we can refer to as a. But then what happens is you resonate the molecule. What that means is you start sending really powerful radio frequencies. So really powerful radio waves are transmitted to the protons, and the protons become energetic. When they become energetic, the protons would go into a high energy state, which is that the protons would start to resonate and they would start to go into the opposing spin, because it requires a lot of energy to oppose the external magnetic field. But if the proton is energetic, if it gains a lot of energy, it would be able to, like the compass needle by default is pointing to the Earth's north, right? If you want to make it point in the other direction, you would have to apply force to it. You would have to give it energy. So that would be the high energy state. So this is that happening. At the quantum level, the proton only has two states. It's either aligned or it's in opposing spin. So if you give it radio waves, the proton starts to go into opposing spin. And that is known as your high energy state. Is that clear as well?
So ये aligned spin का क्या मतलब कि they're pointing in one direction?
No, aligned spin is that they're aligned with the external magnetic field.
अच्छा ठीक है.
Well, that's the default state. Okay, a compass needle by default will be pointing to the planet's north, right?
जी. Yeah.
To make it move in the other direction, you would have to give it energy. You would have to apply some force to it. So high energy state is it's the opposing spin. It's the opposing spin or magnetic dipole.
Sir, not all hydrogens will be in the opposing spin state.
Not all, but they can all. I mean, that is a possibility. So maybe all of them go into opposing spin, right? And remember, resonance would be happening. They would be. So as long as they get these radio waves, they would go into opposing spin, and but they wouldn't be doing this simultaneously. Like maybe this one gets frequencies and it goes into opposing spin. Then it comes back. So that's known as resonance. It would be resonating between the two states, a high energy state and a low energy state. So that's what resonance is. Is that clear?
Yes, sir.
And there's going to be an energy gap. I mean, the proton will not by itself go into the opposing spin. It needs energy from radio waves, and then it's going to resonate. Okay, so hopefully this is what will happen. Like if there is so if there is a powerful magnet and the person goes in, then all our hydrogen protons would start pointing in one direction. But then when you apply radio waves, they would start to resonate. They would start to resonate, and they would resonate between the two states. Okay. Now, this energy gap over here, delta E. Remember, energy is proportional to frequency. So this energy gap is, I mean, it can vary. The energy gap might be very high. That would mean higher frequencies are needed. Or the energy gap would be very low, and that means lower frequencies from the radio waves would be absorbed. So energy is proportional to frequency. Maybe higher frequencies are needed, maybe lower frequencies are needed. So so the thing is that, so what is this energy gap dependent on? But whatever happens, the hydrogen would resonate and absorb very specific frequencies. It's not going to absorb any frequency. It's only going to absorb frequencies that match this energy gap. Okay, is that clear as well? Okay, clear. Simon, is this clear? Ibrar, Bhaskar, Alicia, clear?
Yes, sir.
Yes, sir.
So the thing is that they are not going to absorb any frequency, any random frequency. So what is this energy gap dependent on? Like what factors would be, what are the contributing factors which will either increase this energy gap or decrease this energy gap? So factors that affect delta E, which would in turn affect our resonant frequency as well. So factors affecting delta E. So the first factor is the external magnetic field. So that's factor number one. What do you think? If the external magnetic field is more powerful, would it be easier to go into opposing spin, or would it be more difficult to go into opposing spin? If you had a more powerful external magnetic field.
Difficult.
Okay, so if you had an even more powerful external magnetic field, so let's say the magnet is even more powerful, and there are more magnetic field lines, the flux density is higher, then obviously it's going to become more difficult to go into opposing spin. And that would mean that the energy gap would be bigger. And that would mean that the resonant frequency, or the frequency needed to resonate, would be higher as well. So is that point clear?
Yes, sir.
Munir, is this clear? So
no, sir. I was just trying to process. Well, I mean, I'm trying to process what you're saying, the last part. If you don't mind, if you can repeat it, sir.
the delta E part.
Yeah, the frequency gap and the external magnetic field.
Now I'm just saying that assume that there's a very powerful magnetic field, right?
Mm-hmm.
So it would be, if there's a very powerful magnetic field, this hydrogen proton would get aligned with the external magnetic field, right? Like a compass needle. Is that clear?
Yes, sir.
So it would be much more difficult to actually make it go in or point in the other direction, right?
Yes, sir.
You would need a lot more force. You would need a lot more energy as well, because the external magnetic field is so powerful. Is that clear?
Yes, sir.
So that means, what does that mean? If it becomes harder to go into opposing spin, that means the energy gap is bigger, right?
Yeah.
So if delta E is bigger, that means the frequency that is needed to go into opposing spin would also be higher. I mean, is this part clear, that the energy gap would increase if the magnetic field is stronger?
Yeah.
So now the other thing is that okay, we'll probably continue this next time then. Right now, just remember, we'll talk about factors, TK, in the next class. Right now, just remember that you'll have an energy gap. There's a high energy state, there's a low energy state, there's an opposing spin, there's aligned spin. Your protons would either align with the external magnetic field or would be in the higher energy state, and they would be opposing the external magnetic field. So we'll continue with the factor thing in the next class then, TK. So let's continue tomorrow then.
Thank you, sir.
Sure. Thank you, sir.
Allah Hafiz, sir.
Allah Hafiz.